Okay, so welcome again after a long time. Actually, I am a bit busy, and that is why I could not make videos regularly. Okay, but I will try to complete this series in time. So actually, I forgot that which number it is, which lecture number it is, but that is I think immaterial now. Okay, so let us start with the next topic. So we were studying the various methods of finding the view factors. Okay, so now at this point I would like to remind you that always go back to the basics. Okay, these things are kind of formulae. Okay, but the basic the I mean the basic is what? The basic is these things. Okay, the basic is these things here. So if I copy this, I mean every formula will be derived from this and the basic concept of the view factor algebra. Okay, that is also a basic concept. So I will just paste it here, and now the method that we will be studying is called as the inside sphere method. Okay, inside sphere method. So what does it say? It says that if you have a sphere like this, okay, and in that sphere if you are having two surfaces, okay, maybe one surface is like this, okay, and the surface is like this. So you call this as your surface A1, you call this as your surface A2. Maybe I will join now the centroid of the surfaces. So this is the center, this is the centroid of the surfaces. Okay, now I will join these two, right? So this and also these two also like this. Okay, so we got a triangle. Let me name it as O, A and B. Clear? Okay, so now you tell me that for these two surfaces, if I have to write this equation, my charge of the pencil is going down. Okay, no worries. If the charge is down, I will just explain and I will let the pencil be charged. Okay, so next what we have to do is see the surface normal of A1 is in this direction only. Okay, so this is the direction of N1 cap, right, and this is the direction of N2 cap. Clear? That means from our definition of theta I and theta j, so this will be our theta 1 and this will be our theta 2. Clear? You can revisit the previous drawing also, from there also you will get to know that. Okay, so now if I write this equation here, f dA1 dA2, what I will get? Okay, so I lambda will be cancelled. Okay, so I mean let us not cancel this. So I lambda dA1 dA2, right, cos theta 1 cos theta 2, then s. So here I mean what is the s? S is this distance. Clear? And I can calculate this distance in terms of the r, theta 1 theta 2. So here for sure we can know that theta 1 is equal to theta 2 from this triangle, and this distance that is AB, that is also equal to small s, and that will be equal to what? That will be equal to your 2 into r into cos theta 1, and that is also equal to 2 into r into cos theta 2, and I write it as 2 into r cos theta. Clear? So here if I write it, so this will be 2r cos theta whole square, right, into pi into dA1 into I lambda. Now you see that this term is also nothing but cos theta square. Okay, so that means this equation will boil down to this dA1 dA2 cos theta square, right, then 4r square cos theta square, right, pi dA1 I lambda 1. So which things are for sure constant here? Pi is a constant here, right. Now if I now integrate it, okay, so I will integrate it over the theta, okay, not the lambda, so I can surely cancel out this I lambda. Clear? Okay. And now I mean, let us say that we have to find now what, f dA1 A2, that is a view factor from dA1, that is if this area is my infinitesimal area, this is maybe I will take a small area dA1, from this small area I mean what is the view factor of this large area A2, this finite area A2. So that I will be now calculating. That means I have to integrate over only dA2, wherever there is dA2 I have to integrate over that, right. So over A2, and this will be also integrated over A2, right. Now there will not be any integration because I do not have any A2 here, but for sure now I can cancel out this dA1 thing, right. So next what will happen? See here cos theta square will get out from the integration, right, because I am integrating over this whole area, I am integrating over this whole area. So cos theta square I can take out of the integral, okay. Uh, that means it will be what, A2 dA2 4 pi r square. That means it is coming as A2 by AS, where AS is what, 4 pi r square, that means the surface area of the sphere. Now you see if I have to calculate f A1 A2, that will be what, f dA1 A2, okay, integration of that, okay, with respect to dA1, okay, and also I have to do this one, right, okay. Basically I have to do integration of this over A1 and A2, and in the denominator only A1. I have to do this only there. I mean when I will be finding if A1 A2, I cannot cancel out this dA1 like nothing, right. I have to take that into account. So that is the same thing, but now this thing is coming as A2 by AS. So A2 is a finite area which is constant with respect to dA1, AS is also a constant with respect to dA1. So this I can take out, so it will be what, f dA1 A2 into integral of dA1 by integral of dA1. So that will be cancelled out. That means this is ultimately boiling down to f dA1 A2, sorry, only f dA1 A2, and that is equal to A2 by AS, right. So that means when I can say that I have to find if A1 A2 and A1 and A2 both are inside a sphere, then I can directly write this as A2 by AS. It is immaterial of the area A1, clear, it is A2 by AS, okay. And also why this cos theta square was not important in the integration, okay, because you can take this A2 anywhere, but still this theta 1 will be equal to theta 2 will be equal to theta, okay. So that will not change, and here I have to integrate over this area A2, okay. I have to integrate over this area A2, these concepts are very subtle, so I have to integrate over this area A2. That means this area A2 is fixed when I am integrating over this area A2. This area A2 is fixed. I am integrating like maybe I can consider some strips like this. Then I am integrating, but this area A2 is fixed, and the moment I say that the area A2 is fixed, that means my this normal and as well as this theta 2 is also fixed. Okay, theta 1 and theta 2 is fixed. What I am trying to say is whenever I am I say that I have to find f1 to, that means my area a1 and a2 are fixed. The moment I say that my area a1 and a2 are fixed, I can say that my theta 1 and theta 2 and both are equal to theta, and those are there, that means constant. Okay, okay, and again I am saying that this thing is just a trick. Okay, the basic is that formula only. Similarly, we have something called unit sphere method. Okay, unit sphere method. So what does this say? This says that I can consider a sphere like this. Okay, I can have a surface like this. So I will just consider this part, the upper part. Okay, now what I have to do is, if I have a finite area maybe here, sorry, infinitesimally small area here, dA1, okay, and a finite area here, that is on this sphere. This area can be on at any shape, but this area is on the surface of the sphere. Okay, so this is my A2. So I have to find if dA1 A2, right? Then again I can write this f dA1 A2 as my what? Same thing. So I will just write this thing, that is dA1 dA2 cos theta. Okay, let me just define the things properly. So here I will say that my normal of this area is like this, right? So it is n1 cap, and here this normal will be what? Maybe this is the centroid of the area. Okay, I define this as my centroid of the area too. Okay, so here if I join this, okay, now if I remove this part only, clear, so then I will have this as my n2, clear. Finally I have to join the lines also between the centroids of the area. Now that joining line will be nothing but passing through this. Okay, so this will be the, so if I write this as A, this as B, then AB equal to S. Now my theta 1 is what? This is my theta 1. I should use this color. So this is my theta 1. So theta 1 was there, we got that, and my theta 2 is basically 0 here, right? So if I write this, so this will be what? dA1 dA2 cos theta 1 cos theta 2, right? Anything else I will be cancelled out. I don't think I am missing something. Okay, so a square pi dA2, and there is something called cos, no, that is fine, I lambda. So I lambda will be cancelled out. So here I have to integrate over A2, right? So this will be dA1, sorry. Okay, now again this will be cancelled out, right? So now see what I am getting. I am getting A2, okay, dA2 cos theta, okay, dA2 cos theta 2, okay, into cos theta 1, right, by a square pi, okay. So now tell me that what is this? Now dA2 cos theta 2, I write it as dA2 dash, okay, and I take this a square inside the integral and I finally write as a square into 1 by pi, clear. So and also I can write dA2 dash into cos theta 1 as dA2 double dash, okay. And now if I take this pi again inside, see my solid angle is d omega is some area dA by some distance square. So this is some solid angle, this is any solid angle, I mean this is a solid angle, okay. So we define for our simplicity, for our problem solving purpose, this as d omega dash and by pi. So this whole thing boils down to this d omega dash by pi, okay. Now see, for this particular problem you have, your theta 2 equal to 0. If your theta 2 is equal to 0, then your d2a dash is equal to d2a, sorry, da2 dash is equal to da2, and my cos theta 1 you can find. If you know this this position of b, you can find. Thusly you can find this da2 double dash, and also you can find this a square, maybe in terms of theta, okay. So this is also a technique, but having said that, I must warn you that these techniques will not simplify your life for any problem. Like for this problem I have a good sphere, I have a very beautiful sphere, but if I had a surface or maybe I was not having a sphere, or maybe this surface, this dA1 is located somewhere like this, okay, then see again its normal is like this only, n1. But now you see your theta 2 will not be 0, because I have to join like this, and this normal is also again same, but then this is your theta 2 and this is your theta 1, okay. Then your life will not always be simple if you use these tricks and techniques. So you have to be very judicious when I mean you will be using these techniques, okay. Okay, so now I will not teach view factor anymore, okay, and further I mean we will be solving some more maybe problems regarding the view factor, and the application of this thing will come forward when I will be teaching you the next topic. So the next topic is the radiation heat exchange between surfaces. Now when I say surfaces, then I can cover very broad area. If I say real surface, okay, so now let me charge my pencil, okay. So when I say real surface, that means I can cover a very broad area. It can be, I mean the surface properties, that is absorptivity, reflectivity, emissivity, all can vary with wavelength as well as directions. So for that the analysis is very complex. That is why what we will do here, the analysis for the gray diffuse surfaces, okay. So let me have some water. So we will do the analysis for the gray diffuse surfaces, okay. So the next topic is radiation heat exchange between gray diffuse surfaces. Clear? Okay, these lines I am not liking, it should be a bit straight. Okay, gray diffuse surfaces. So there are various methods. Okay, the first method that we will be studying is, okay, solving simultaneous equations. So first understand the problem. So we will have an enclosure. Not in all the problem we will have the enclosure. So I mean, what do I mean by an enclosure? Enclosure means some collection of some surfaces oriented arbitrarily. Okay, that means I can have an enclosure like this. So this enclosure means what? Enclosure means it is enclosing something space, some space. So it is enclosing this space. Okay, I can also have an enclosure like this. And what is the difference? So in this enclosure, these are some different surfaces. Okay, so these are discrete surfaces, or I can call this as a discrete enclosure. But here this I cannot divide, and I mean, when I can divide and I can say that this is I mean, this is a separate surface, I can only say that this is a separate surface when throughout this surface the radiation surface properties are the same. Okay, so maybe for this I have emissivity, I mean yes, emissivity as epsilon 1, alpha 1 as absorptivity, rho 1 as reflectivity, tau 1 as transmittivity, and for this surface maybe I am having emissivity as alpha epsilon 3, absorptivity as alpha 3, transmissivity as tau 3, and I mean reflectivity as rho 3. Clear? But for this surface I cannot say that I have separate surfaces like that. Okay, so this is a continuous surface. Now what I am telling is that if I have a, a vector like S here, so this vector is traversing the path along this one, along this surface. So my all the properties like, sorry, all the properties like this, maybe epsilon is a function of S, or I should say that if I have a coordinate system where this is O, and if I take an infinitesimal surface element here, and maybe R is the position vector of the surface element, then my epsilon is a function of R. Okay, so it is continuous. Okay, so this is a continuous enclosure. So this is a continuous enclosure, and this is a discrete one. Okay, so we have to find what? So for any continuous enclosure we have to find that if I take up any arbitrary part here, maybe I take that as A1, so I have to find that I mean, what is Q1 or capital Q1? Okay, so capital Q1 is the net radiation energy, okay, flowing through A1. Clear? And for that I have to find Q1, because capital Q1 is equal to small q1 into A1. Clear? Okay. So net radiation energy flowing through A1. Fine. Okay. Now let us see that how can we do that. Okay. So now I am saying that solving simultaneous equations. So you will soon come to know that why this method is known as this. Okay. So let me first talk about the now. Okay. So now let me introduce you the concept of radiosity. So what is radiosity? So consider any surface. Okay, consider any surface like this. Okay, if I directly ask you that what is the amount of radiation energy leaving the surface? Okay, so I am writing it net or okay net it is fine. Net amount of radiation energy leaving the surface. Then some of you will directly jump and say that okay, I know that is my epsilon into EBT. If the surface is at a temperature T, then it will be epsilon into EBT into the area of the surface, and the surface is having emissivity epsilon. But now I will argue with you that here some radiation energy can come, okay, and this I called as irradiation. So this I say as H. Okay. Now if this is coming, then this surface is also having a property called rho or reflectivity. So due to a non-zero reflectivity, what I will have? Due to a non-zero reflectivity, I will have a maybe I should do it with red. I will have rho into H, right? That means net amount is not only this epsilon into EB into A, but this will also include this rho into H into A. Okay, that means this will be this one plus rho into H. Okay. Okay. Now this term, that is net radiation flux. Okay, net radiation flux, and that is equal to J. Okay, and this is called as radiosity. Fine, this is called as radiosity, right? So you can see that even if I can say that my emissivity is not a function of maybe lambda, but my rho can be a function of lambda. Okay, or my emissivity and rho that can vary differently with respect to lambda. Okay, so summation of that will dictate that the J. Okay, that means what will be my radiosity. Clear? Okay. So, and for gray diffuse surface, now I can write, okay, for gray diffuse surface, or I can directly write for a diffuse surface only. My J is J lambda is equal to I lambda into pi. This is the same analogy. Okay, when I derive this EB lambda equal to I lambda into pi, the same analogy. Okay, so I mean when I say my gray diffuse surface, then this then I have to integrate it over the solid angles, and my EB and H will not depend on the directions. Okay, so that is why I can take out those in from the integral. I mean the same procedure. I mean the same procedure when we proved this one. Okay, so I am not doing it again. Okay, so fine. Now you would tell me that what will be my Q, and Q is my net. Okay, so here I should not write net radiation flux, net emittive radiation flux I should write. So net emittive or net outgoing, because I have already have a property called emissivity. So outgoing net outgoing radiation flux. So if Q is my net radiation flux, then I can write it as my J, right, minus what is being absorbed, right. J is total emission, okay, minus or J minus H, right. Array. Okay, J minus H, okay. So will it be only J minus H? Yes, that is correct. So J is the net radiation flux that is going out, and H is the net radiation flux that is coming in. Okay. Now you can see that I can also write this as my EB lambda into epsilon minus alpha into H. Alpha is absorptivity, clear? Alpha is absorptivity. So now see, if I from these two equations, what I can do is I can eliminate this H, this irradiation, okay. So that means if I have to do that, what I will write? I can write Q, so okay, so alpha Q is also equal to J alpha minus alpha H, right, and also I have Q is equal to epsilon into EB minus alpha H. That means I can have Q minus alpha Q is equal to epsilon into EB minus J alpha, clear? Now for a gray diffuse surface, so all these things I am talking about a single surface. For a gray diffuse surface, alpha is equal to epsilon, I can take that out, epsilon, so EB minus J, and I can have this as Q into 1 minus alpha, and alpha is equal to epsilon for a gray diffuse surface, okay. So that means my Q is equal to EB minus J by 1 by epsilon by epsilon. This formula you already have heard in your B.Tech heat transfer course, okay. And in the next lecture, we will learn the the electrical network analogy of the radiation heat transfer. There you will see that this we call as the surface resistance, okay. Sorry, the space resistance, not the surface resistance. Okay. So I hope this analogy is clear. Now what we will do is, from here we will directly write the J in terms of Q and EB. And why are we doing that? The simple reason is that for different surfaces we need to generally find the heat fluxes or the temperature. Now this thing is a function of temperature and this thing is heat flux. So what I have said right now, that in any radiation heat transfer problem regarding the enclosures, we need to find the temperature of any surface, and that is governing by this term EB, and also we may be asked to find the heat flux, and that is nothing but this. So that is why we don't need this J radiosity, and that is why I will be writing J in terms of Q and EB. So J is equal to minus Q plus EB, right? Or I can write this as Q into 1 minus 1 by epsilon plus EB. This is for a single gray diffuse surface. This is a very important result. Okay. So I hope up till now this derivation is clear, right? Now some of you might argue with me that why are you not writing this thing? I mean, if I am talking about the net radiation flux, then this should be J. Okay, this should be J, and this should be minus alpha H. No, when you are talking about J, you have already taken care of this alpha H, because J is what? J is epsilon EB minus C minus what? Sorry, plus what? Plus rho into H. That means this will be 1 minus alpha into H if the transmittivity is 0. So that means this will be this minus alpha H plus H. Now you see my J minus H is equal to epsilon into EB minus alpha H. Okay, and this is equal to my Q, the net radiation flux. Okay, so I mean, see, the definition should be very much clear. What do I mean by the net radiation flux? If I have a surface like this, so you consider this as a black box. So you consider this as a black box. You don't know that what this black box is eating and what it is emitting. You can only see that something called H is coming and something called J is going. That means the net radiation heat transfer through the surface is what it is getting minus what it is emitting. So that is why it is J minus H. Okay. I mean, if I have to know that the net amount of the thing that it is emitting, that means what it is totally emitting minus what it is getting. Now inside what is happening, that you don't know. Okay, that we know, but I mean that is the logic behind writing this J minus H. Okay, and I have also shown you that this J minus H, how it is equal to this thing. Okay, so I think all are clear up to this thing. Okay, so now let us consider an enclosure, that also a continuous enclosure. Okay, so this is our continuous enclosure, and by now you already know that what do I mean by a continuous enclosure and a discrete enclosure, right? That you know. So continuous enclosure means what? It is having effectively only one surface, right? So what we need to do is we need to prescribe the temperature variation and the heat transfer variation. That is, what I can say is, so first let me do it very systematically. Okay, so first I will draw a coordinate axis like this. Okay, so x, y, z. Clear? Now let me take any infinitesimally small area and effectively it is a point. So this is a area, small area, infinitesimally small area having magnitude of dA, and the normal is also I can specify, okay, in this direction maybe, and the magnitude is dA. Clear? So now what we can draw is a position vector, right? We can draw a position vector r. Okay, so effectively as engineers we need to know that what is the temperature there and what is the heat flux there, right? We need to find q, okay, q, that is a function of r here, and also the temperature, that is a function of r here. Okay, effectively if we can find, see, if we can find EB, that is a function of r here. So why these are functions of r? Because this will vary throughout the surface of the enclosure. Okay, and we know that EB is equal to sigma T to the power 4. So if we know EB, then we know this T, right? So we need to find these two. Okay, so let us see how can we do this. As I said earlier, there are so many methods, and currently we are considering solving simultaneous equations. So we need to build those set of simultaneous equations. Okay, so let us try that. So firstly, let us see that how can we find q. We will go step by step. How can we find q? So q is net, actually heat flux, but here we will be considering only radiation and not convection or conduction. So net radiation heat flux going out of the surface. The moment I say going out of the surface, see, I have drawn the normal like this, but enclosure means I am interested in the inside. Okay, I am interested in the inside, so maybe my normal is like this. Okay, so anything that is going out, that means this is my direction of q. Anything that is coming in, that is like this. Okay, so q is what? Already I have told that q is equal to, so net that is going out, so j minus h. So we, by this time we know that this is what we call as radiosity, and this is what we call as irradiation. Please note one fact, that all these things are having the units of watt per meter square. I mean, it can be also kilowatt per centimeter square, but what I am trying to emphasize it is that I am considering all these things per unit area, flux. Okay, so if I have to find q, I need to know j and h, right? So let us try to find the h. See, when I am deriving all these things, I am trying not only to show the steps, but I am trying to also convey the thought process. That is, we need to derive Q and we need to find Q and T as an engineer. Then Q is equal to J minus H. Now I need to find J and H both to find Q. So let us see. So H is equal to what? So H is equal to irradiation, the total amount of radiation energy that is coming on this Chuttusa area dA, right? So what will be that? So one thing will be that if anything is coming from the outside of the enclosure, that we call as HO, that is a function of R. That is out, that is incoming radiation coming from out of the enclosure, that is why I have put the subscript O here, and that is also coming on a infinitesimally small area dA at a position vector r, that is why this r is here. So it has two parts, one is this HO and that is a function of r, okay, plus everything that is coming, okay. So irradiation I should write, or radiation energy coming from the enclosure itself, from the enclosure. Up till this I hope everyone is clear. So now let us find this part. How can we find this part? Okay, so let us consider any other area, infinitesimally small area than this. So I will consider this area here, okay. This area is having a magnitude dA dash, okay, and also this area is having okay, with this color only, this as r dash, the position vector, and the normal as n dash cap, right. So what will be the energy, emitted by this dA dash area surface? So that is the radiosity at this point, right. Now it will emit some total energy, that is J, and which is a function of r dash, but out of this energy a part only will be intercepted by this one, and that will be governed by which term? The view factor between this and this. Likewise, there can be infinite number of infinitesimally small area, right. So from all these energies will be going, so we need to integrate this J into F dA dash dA, okay. This is the total energy that is going here, right. And if I say only the flux, then this dA dash will not be there, that is fine, but this is the total energy that is going here from this area dA. And if I have to consider the total energy coming from the enclosure to the surface dA, I have to integrate it over the enclosure surface, ES, enclosure surface. I hope this is clear. Now see, if I need to know the total irradiation, then I have to write actually H into dA, because H is per unit area. So this will be H naught R into dA. Now plus, now we know that J is the radiosity and that is a function of R dash, right. into F dA dash to dA. So this is per unit area, so I have to multiply with dA dash. This I have to integrate over the enclosure area. I write this as capital sigma. Okay, so capital sigma is what? I am also writing that capital sigma is the surface area of the enclosure. Clear? So now let us proceed. We will use the reciprocity rule, and why we will use that I will tell you right now. So by reciprocity rule we can write this guy as, okay, so I will use this guy as F dA to dA dash into dA. Clear? So that means finally I can write this is equal to this thing plus j, that is a function of r dash F dA dash into dA over sigma. Okay, so effectively this is the total irradiation energy coming from the enclosure itself, right? So if I have to find the irradiation energy coming from the enclosure per unit surface area dA, then that will be what? So I can write H is equal to H naught, that is a function of R. Okay, actually this H is also a function of R. Okay, plus J, that is a function of R dash and not R, F dA dash. Clear? So we have found the H. See, we cannot write that I have cancelled out this thing. I mean I cannot say that I have cancelled out this dA, because this dA is the part of this integration. Okay, but still I can write this. How? I mean this is also correct and this is also correct, but I cannot get this from this, like cancelling this dA, but still it is right. How? So this is the heat flux, or the not the heat flux only, this is the radiosity flux coming from the enclosure to the surface dA. Okay, so if you say that what will be the correlation between this and this, so if I have a finite amount of area, then I can write that this guy into that finite amount of area is equal to integration of this guy, this and this dA, integration over that area. Okay, and here I got a mistake, that this will be not actually sigma. Okay, this will be not sigma. Okay, now let us see, we have found the H, right? So let us box the equation. Why is this not sigma here? Because sigma was the limit for this A dash. Okay, but now I have dA, this is not sigma. Okay, so this is H. So if I now put this into my Q, so my Q was j minus h naught, or I should write it in a very formal manner, q, that is a function of r, that is j, that is also a function of r, minus h naught, that is a function of r, minus j r dash f dA dash. Clear? Okay. So now what I can get? Let us see. So now see, I need an equation only containing q and t, because I want those. Okay, but here I have q and j, so I need to replace j. This is the thought. Process by which we should proceed. So j, we have already done this. So j is equal to q into 1 minus epsilon, 1 minus 1 by epsilon by EB. So j is equal to EB plus q into 1 minus 1 by epsilon, or I can write it as EB minus q into 1 by epsilon minus 1. Okay. So, or I should write that j r is equal to EB r minus q at r into 1 minus epsilon at r, sorry, 1 by epsilon at r minus 1. If I put r dash, everything will be r dash. Now here in this equation I will use this equation to replace this j at r and j at r dash. Okay, so let us do that. So q at r is equal to EB at r minus q at r into 1 by epsilon at r minus 1, okay, minus HO at r minus integration of EB at r dash, right, minus q at r dash 1 by epsilon at r dash minus 1 into f dA dash. Right? Okay. So effectively this is our final equation, but here I will write this q in one side. Okay. If I take qr common, then I will have 1, and I will take this fellow in this side. So I will get 1 minus, so let us do it very carefully. So 1 plus, right, 1 plus 1 by epsilon at r minus 1, right. So I will also take this irradiation in the LHS, okay, just for simplicity, and this is equal to EBR, okay, minus these things. So I will write these guys separately. So f dA dash integration of that, and plus q, okay, plus q into, or what, okay, so let me first write it. This one minus this one, f dA dA dash. I hope I have not made any algebraic mistake. Now I will put all the q in one side. So what I will do is I will copy the whole thing, but now I will move this fellow a bit. Okay, this whole fellow a bit here. I will move this guy here. I will okay, sorry about that. These are okay, so I think, or let me cut it and I will paste it here in a smaller version so that I can fit it. But now this will be minus, okay, and here there will be only these guys. So this is the final equation, and I am only having q and e here, and this e is I mean representing the temperature, okay. Now this is for a continuous enclosure if I have a discontinuous or discrete enclosure having n surface, okay. Now the same equation I will just convert it, okay. So for an enclosure having n surfaces, okay. So now you can say that for any surface, how can I define q? Because if I have a finite surface, okay, so I mean if this is my finite enclosure, then on this surface how can I define q? Because at every point q can vary on the surface also. So actually for any surface, so maybe this is the ith surface, okay, this is the ith surface. So heat flux qi at ith surface is equal to, it is something like an average heat flux. So this is the area of ith surface by the area of ith surface, okay. This is actually some average, so I should okay, so let me write this as q dash, okay, okay. So this is some average, and if this q is uniform throughout the surface, then this is equal to q dash I, okay. So considering this equation, can you tell me that what are the only change that I need to make? So first let me again copy this equation. So copy, paste, okay. So I need to find qi, heat transfer at ith surface. I can be any number from 1 to n, right? So I need to find qi, so let me write it with this color. So this qr will be here qi, okay. So this I, so this r means I here, I mean, so see this r means any position vector for any point. Now here I have discrete surfaces, and for a continuous enclosure all the points were behaving like the discrete surfaces. So here this r was playing the role of this I, Am I clear? This r is a position vector of a point actually, and this point is behaving like a discrete surface for a continuous enclosure, and here this I is behaving like a, I mean here not behaving, here this I is the index for the ith surface. So this r and this I are equivalent actually. Okay. So okay, so now there is no meaning of write this once because this will be cancelled out, right? So I can write this only. Okay. So by epsilon I minus, okay, so now there was the integration, and this integration will be over not I but anything other than I, maybe any other index I will take as j. Okay, so j can be equal to 1 to n, because if a surface is itself like this, then some radiation energy emitted by this ith surface can go back to itself also. So that is why this j will also contain this I. So this will be equal to now q. Now see, this is here r dash, that means I need to take some any other coefficient j. Okay, if I consider this enclosure, then maybe this is my jth surface. So for this ith surface, if I consider, if I have to find the irradiation, the radiation energy that is coming from the enclosure, then I have to find that from this surface how much energy is coming, from this surface how much energy is coming, from this surface how much energy is coming, from this surface how much energy is coming. And if this surface was like this ith surface, then from this surface itself how much energy is coming. So I need to find an expression of the energy that is coming from jth surface, and I need to sum up over all the surfaces. That is why this is j equal to 1 to n qj and what 1 sorry qj into 1 by epsilon j minus 1 f. Now dai daj. Okay, okay, fine. So plus now HO R was there, so that will be subscript I. Okay, is equal to EB I, because there is R, minus, so again this will be integration over J equal to 1 to n EB J F, or now I don't need to write dA. Okay, so these are finite areas. So AI AJ, this is also AI AJ. Clear? So this is the final equation for the enclosure, and this has got one more form, that is equal to, see, if I multiply here 1 EB into 1, that is not a crime, right? So, or I am writing it actually directly. So EB1 is equal to EBI is equal to EBI into 1. Now I know that my summation if AI AJ over J equal to 1 to n, that is also equal to 1. You can visit the previous lectures, I have explained it. Okay. So that means I can write this is equal to, let me move this here, okay, and let me write it very formally actually. So this will be inside the bracket, and I can write this fellow as, so EBI minus EBJ common lacquer, I will write this. Okay, fine. Okay then. Sorry, I have done a mistake. This summation should be outside the whole thing. Let me write it again. Let me do it step by step. So EBI is equal to summation of EBI. I can write this as into FAI AJ. Right, because this is I, this is independent of this J, so I can take inside this. Okay, so J is equal to 1 to N minus EBJ F AI AJ. Clear? So this is also over J equal to 1 to N. So J is equal to 1 to N, right? EBI minus EBJ into FAI AJ. Clear? So see, this is the equation for ith surface. Okay, so let me just box it with a bright color. Okay, this is the equation for ith surface. If you have 4 surface, 5 surface, you can have n number of surface in enclosure. So from that you can get n simultaneous equations. Simultaneous equations. You have to solve them to find either Q or EB. Okay, either Q or EB, either QI or EBI. Okay. Now a simplification. Okay. So for a black enclosure, okay, for a black enclosure, or maybe I should write for an enclosure having black surfaces. Okay, for an enclosure having black surfaces. So black surface means what? EI is equal to 1 for all I runs from 1 to n. Okay, this is the notation for I runs from 1 to n. Okay, so let us copy again this equation and paste this here. Okay, so I will just remove this, sorry, this and this. Okay, so here I need to put epsilon I equal to 1. So let us put that and let us see what we will get. Qi minus, so this will be 0, the second term. Okay, so Qi plus HOI is equal to EBI minus this one EBJ if AIAJ, or I can write the second form Qi plus HOI is equal to summation over J EBJ if AIAJ. Okay, so this is the equation for a black enclosure. Okay, this is the equation for ith surface of an enclosure having black surfaces. Okay. Okay, so now in the next lecture, I will solve some mathematical problems and I will show you that how to apply these equations. Okay, I mean how to apply these equations to find Q and EB. After that, we will learn the thermal network. But now I will give you a homework, that is, I have simplified this large equation, this general equation, to get this equation. But now you have to consider a black surface. This is an enclosure having black surfaces, that is epsilon I equal to 1 for all I runs from 1 to n. This I know, and I have n number of surfaces, so I should ideally draw it like this. Okay, dot dot dot. So this is 1, 2, 3, this is n. Okay, so dot and dot dot dot. Okay, so you need to find this expression, you need to prove this expression starting from the scratch, that is Q is equal to J minus H, and you need to also, I mean the thing that I have done, that is you need to find the integral equation first, then you need to convert it to the summation equation. That is, if it was a if it okay, sorry for that, my father actually came. So if it was a continuous enclosure, then also derive the equation, from that convert it to the summation form. Okay, that is your homework. Okay, so up till that, goodbye, take care and thank you, and we will meet in the next lecture.